Welcome to this explainer. Today we're going to uncover exactly how ancient societies mastered the raw, chaotic power of fire to actually build a civilization as we know it. It's this incredible journey from basic survival all the way to early science, and I absolutely can't wait to share it with you. Let's get started.
All right, let's kick things off by defining our core term here, pyrotechnology. What does that actually mean? Well, we are moving way beyond just cooking dinner or keeping the cave warm. We're stepping right into the realm of ancient chemistry. Pyrotechnology is all about the deliberate control and manipulation of fire to achieve these massive, high-temperature processes. We're talking about manufacturing inorganic artifacts like ceramics, glass, and early metals.
There's a great quote here that perfectly captures what early humans were grappling with. It notes that fire is a chemical reaction that occurs when fuel, heat, and oxygen are present in the proper ratio. If the ratio of fuel to oxygen is changed, there will be a consequent effect upon the heat generated. Early artisans realized that fire wasn't just heat or magic, it was this delicate equation. By messing with the ratio of fuel to oxygen, they found they could radically alter the heat generated. Basically, they became the world's very first chemical engineers.
So here's our roadmap for today. First, mastering ancient fire. Second, the pyrotechnology recipe. Third, kilns, hearths, and furnaces. And finally, reading the burnt clues.
Let's dive right into part 1, mastering ancient fire. The crucial takeaway here is the massive technological leap early humans made. Think about organic processes, things like roasting meats or drying grains. These generally happen at pretty low temperatures, under 500 degrees Celsius, and you really don't need highly specialized structures to pull them off. But then, compare that to inorganic processes. To make ceramics, melt glass, or extract metals from solid rock, they needed sustained, punishingly high temperatures, sometimes pushing all the way up to 1,500 degrees Celsius. Achieving that was an absolute game changer for human history.
Which brings us to part 2, the pyrotechnology recipe. To act as ancient chemists and hit those insane temperatures, these early engineers had to master a very specific recipe, balancing 3 demanding variables. First up, fuel. They weren't just chucking random twigs on a fire. They meticulously selected wood, charcoal, peat, or coal based on its specific calorific value. Second, temperature. This definitely wasn't a set-it-and-forget-it modern oven. They needed dynamic control, constantly adjusting the heat throughout the entire process. And third, they had to control the atmosphere inside the fire, specifically the oxygen levels.
Now, atmosphere control is absolutely fascinating. We usually just assume a fire needs as much oxygen as possible to burn hotter, right? Well, that's called an oxidizing atmosphere. And while it's great for firing clay, extracting actual metals from raw rock ores requires the exact opposite. They had to intentionally starve the fire of oxygen to create a reducing atmosphere. This kind of environment is incredibly rich in carbon monoxide, which literally chemically strips the oxygen away from the metallic oxides, leaving behind pure metal.
To see just how dynamic and difficult managing this was, just look at this temperature profile of an experimental iron smelting furnace. Notice those wild fluctuations over a 7-hour period? The temperature drops when raw ore is added, and it sharply spikes when the airflow is adjusted. Maintaining this delicate, dangerous dance inside a roaring furnace relied entirely on the artisan's skill. Often they were just judging things by the exact color of the flame.
Let's really put this into perspective, because the numbers are wild. Baking clay takes around 200 degrees Celsius. Melting copper, that demands a blistering 1,086 degrees. And the vitrification of clays, which is essentially turning clay into glass, requires pushing way past 1,500 degrees. When you consider the sheer scale of heat required here, hitting 1,500 degrees Celsius using nothing but mud for walls, wood for fuel, and forced air from hand bellows, it is just an absolute triumph of human ingenuity.
Moving on to part 3, kilns, hearths, and furnaces. Here we can track their structural evolution. They started out with simple open bonfires. Now, while a bonfire can reach 1,000 degrees, it offers absolutely zero control over the atmosphere. You're entirely at the mercy of the wind. To progress, they developed the hearth and the enclosed kiln, reaching 1,300 degrees with medium control. And finally, they engineered the furnace. Capable of hitting 1,500 degrees, the furnace provided the strict degree of control over that crucial reducing atmosphere needed to truly conquer metallurgy.
Take a look at this excavated 14th century clay shaft furnace from North Yorkshire. It shows exactly how these structures were engineered. Notice how it's built directly into the slope of the hill? That wasn't just for convenience. It was a highly deliberate design choice to perfectly manage the airflow and allow the heavy, molten liquid slag to be tapped and safely drained out the bottom via a specialized arch.
Sometimes, this need for heat completely took over domestic life. Just look at this plan of a 12th century longhouse at Criff Farm in Cornwall. Originally, it was just a regular home, but it got radically adapted for industry. They actually built a waist-high forge right against the inside wall and dumped massive amounts of tin smelting slag just outside. Imagine transforming your own living room into an industrial metallurgical facility. But here's a massive plot twist for the archaeologists studying all of this.
Which leads us to part 4, reading the burnt clues. You see, most of these ancient machines didn't actually survive the centuries, so archaeologists have to be meticulous scientific detectives. As the source text warns, just finding some evidence of burning and a tiny bit of slag doesn't automatically mean you've discovered an advanced ancient smelting operation. It notes that the structure must be rigorous. The temptation to interpret evidence for burning plus a few grams of slag as a smelting site must be resisted. Otherwise, you might just be looking at the remains of a really hot campfire.
So, instead of relying solely on structural remains, experts rely heavily on slags and residues. What are those? They're basically the inorganic waste byproducts of pyrotechnological processes. Think of it as the solidified, burnt industrial trash of the ancient world. But to an archaeologist, this trash acts as a definitive chemical fingerprint that proves exactly what was happening at that site hundreds or even thousands of years ago.
Experts use a sort of archaeological cheat sheet, differentiating these residues into 2 categories. On one hand, you have diagnostic residues like tap slags or smelting slags. These are the smoking gun. They absolutely confirm a specific process, like iron smelting, took place. On the other hand, you've got non-diagnostic residues, like charcoal or bits of fired clay. On their own, these could be from a high-tech furnace, or they could just be from a domestic house fire. They require a lot more context to be useful.
The really crucial point here is how archaeologists track this waste. Large chunks of slag were basically industrial garbage, and they were often dumped far away from the actual furnace, meaning they're usually found in secondary locations. But the real gold mine? Microslags. For example, tiny, microscopic flakes called hammer scale that literally pop off hot iron when a blacksmith strikes it. Because they're so small, they fall straight to the floor. Finding them during careful soil sieving is actually the very best way to pinpoint exactly where an ancient blacksmith stood.
So this leaves us with a really fascinating question to wrap up our explainer. We rely heavily on decoding the industrial trash of our ancestors to understand their greatest technological triumphs. But if our modern society vanished tomorrow, what specific industrial trash, what diagnostic slags would future archaeologists dig up to decode our own technological secrets? It really makes you look at our everyday waste in a completely different light, doesn't it? Thanks for exploring this with me today, and keep questioning the world around you.